Hi everyone! Today we're working on photoelectric effect. We have done all the topics in this unit, Unit 10, except for how to do the calculations pertaining to photoelectric effect. One way you could imagine photoelectric effect is imagine you've got some sort of hole in the ground, right? At the bottom of the hole in the ground, there is a person kicking an electron soccer ball. The person is going to represent the light. And the red light gives the electron a little bit of a kick. It might roll it part of the way up the hill, but the photoelectric effect doesn't occur because the electron, maybe it gets to a new energy state, doesn't make it out of the atom. For this reason, you'll sometimes hear people refer to atoms as energy wells, because you have an electron that it needs to get out of the well in order to have the photoelectric effect. So now, let's say we're keeping with that analogy. We've got this hole in the ground here with a person at the bottom representing the light and an electron soccer ball. Except now, more energetic light comes in. If blue light comes in, blue light having both higher frequency and higher energy than red, might give this electron enough of a kick to be able to not only leave the well, but proceed on its way with some kinetic energy left over. Now, let's bring this back to a while ago. We have kinetic energy at the end picture. We have light at the beginning picture. This would be a really good place to start thinking about our energy transformations. On one hand, at the beginning of the picture, we had light energy. Light energy came into the atom with no kinetic and no potential energy. Afterwards, the electron wasted some of its energy getting out of this potential well. It had electric potential energy that it had to overcome, and whatever is left over becomes kinetic. Items in this energy state would be the electron, the atom, the light. And so we're going to have an equation here. I'll put it in a different color with a little X around it so we can see it. In this case, the energy of the photon coming in is going to be equal to the kinetic energy of the electron leaving. But instead of calling this electric potential energy, remember we called this work function yesterday. And work function symbol is a lowercase phi. So this is the photoelectric effect equation. But think of it to yourself as it's basically just a conservation of energy. The light energy going into the atom resulted in some amount of potential difference. So it increased in potential energy as it went up this potential well. And whatever energy is left over is kinetic. This green equation, the light going in, is giving this electron a kick of 2.1 of them are used up in getting out of the atom. It's used up by the work function, and so the remainder is kinetic energy. So let's see if we can fill it in on this chart here. 8.28 is the initial energy of the light. The work function was 2.12. So how much kinetic energy is left over? It should be 6.16 electron volts left over. So how would this work practically? So let's say I give you an example problem. And let's say I give you light with a frequency of 2 times 10 to the 15th hertz. This is in the ultraviolet area of the spectrum, high energy, high frequency light. And let's say that this is some sort of atom. Let's say it's cesium, whose work function is 2.2 electron volts. Let's say I want to use to calculate how much kinetic energy does the electron have at the end. So what I want to do first is I want to calculate the energy of the photon, then use the work function and subtract to get kinetic energy. So, my students asked me this question today. I figure it's probably a pretty useful question if enough people asked me. How do you calculate the energy of a photon? I'm going to need it in order to calculate the kinetic energy, so try this for me. Energy of a photon can be calculated in one of two ways. I could either use Planck constant times frequency, or take hc over lambda. And someone was asking, how do you tell which of these to use as a first step to solve this problem? Well, since I don't have a wavelength, I want to use that first equation. So step 1 to solve this problem. Calculating the photon energy is going to be equal to taking Planck's constant times the frequency. So Planck's constant is 4.14 times 10 to the negative 15th electron volts times seconds. The frequency given in this problem is 2 times 10 to the positive 15th, so those exponents cancel out. And the energy of the photon is 8.28 electron volts for the energy of the photon. So, 28 electron volts. So, in this case, if I want to apply my new photoelectric effect equation, I first calculate the energy of the photon, then take the work function and subtract to get kinetic energy. 8.28 electron volts is equal to 2.12 plus kinetic energy, subtract to the other side, and that's 6.16 electron volts of kinetic energy left for the electron. So, I want to give you one other common representation that you might see, and that's a graphical representation. You might have noticed this in the homework from yesterday. So, in addition to being able to use the photoelectric effect equation, you should also be able to understand this graph. Let's say that I have the photoelectric effect occurring for a certain metal. You'll see this on the review packet for practice for homework tonight. Let's say that I have certain frequencies of light that result in kinetic energy of your electron. For low frequencies, and all my frequencies are going to be power 10 to the 15 here. 2, 3, 4, 5, 6. Let's say that I have no electrons, no emission for 1 times 10 to the 15th frequency. No emission for 2 times 10 to the 15th frequency. And I get really slow emission for a frequency of 3 times 10 to the 15th. What this means is I have a function that looks something like this. 0, 0, 0, 0. And at some point, it turns over and has this inflection point. We call that the cutoff frequency. And to figure out where that is, I actually need to give you the next data point. Let's say the next data point is at 0.5. Okay. So, where's the cutoff frequency? I know it's somewhere between 2 and 3. But what I would want to do is graph this out, plot backwards, and wherever this line intercepts the x-axis is my cutoff frequency. My cutoff frequency is the minimum frequency you need in order to have any electrons come out. And it's actually very closely related to the work function. In fact, let's say we plotted our line. Erase that. Let's say we plotted our line. If we extended red backwards, the y-intercept of this graph would give us the work function. So let's say for this particular data set, let's say for this particular metal, it has a cutoff frequency of just over 2. It would have a work function that's equal to the y-intercept. So let's just label those real quick. Work function is the y-intercept. And I'm absolute valuing here, so even though it's some negative number, the work function will be positive. And the cutoff frequency, the minimum frequency that you need in order to have electrons come out, is the x-intercept. So let's say we plotted a different metal. A different metal would have a graph that looks identical, except might have a different cutoff frequency and a different work function. Notice that as your cutoff frequency increases, your work function also becomes a larger magnitude value. One thing we didn't get a chance to talk about is where we actually measure Planck's constant. If we were in class and able to do this lab, we would have been able to study this for different LEDs, and the slope of this line is actually equal to Planck's constant. So, no matter what metal I use, these slopes should be parallel to each other, but with work functions and cutoff frequencies that are proportional.